Good afternoon, everyone. I am Arghadip Das, and I will be presenting a part of our work on an efficient design for a hardware accelerator for hidden periodicity detection using Ramanujan sums. The following slide contains the outline for our presentation today. Periodicity detection of any discrete time signal x of n deals with finding a p for which x of n will be equal to x of n plus p, even p is the smallest of such numbers. A part of our work two or more different different signals can combine themselves to form another signal with a different periodicity. In such cases, the periodicity of the basic signals are termed as the hidden periods. The period estimation problem, which can be defined as estimating the periodicity, including the hidden periods, for any noisy signal having a time-varying periodic nature, is shown to have an elegant solution using Ramanujan filter banks. We use the same to construct our hidden periodicity detector. Here we show a basic hidden periodicity detector in action. Ramanujan filter bank RFB based on Ramanujan sums was introduced as a tool for identifying periodic patterns in data. RFB based periodicity detection was shown to have computational advantages over other methods and also reveal localized hidden periodicities in real-time data and process signals with time-varying periodic nature. It was also shown to be of interest in real-world applications like detecting seizures using EEG data or to identify repetitive structures in protein molecules, etc. Our motivation was to design and implement a fast, cheap, and energy-efficient hardware accelerator for hidden periodicity detection based on RFB. Now, we take a very brief look at what is Ramanujan filter bank. Ramanujan sum is a trigonometric summation defined by Srinivas Ramanujan, defined as the summation of e power j 2 pi kn by q for k equals to 1 to q, where k and q are co-prime integers. RFB was a compact approximated representation of the use of Ramanujan nested periodic dictionaries to solve the periodicity detection problem, represented by a group of filters from 1 to Pmax, Pmax being the maximum period which can be detected, with each filter having the impulse response of HPN. Here, L is the number of periods of CPN. The following structure shows the construction of the periodicity detector, which was proposed using the Ramanujan filter bank by Vaidyanathan et al. The output for each channel corresponds to the strength of the corresponding period in the input. We first propose a basic microarchitecture for the HPD based on RFB, which we improve upon with incremental modifications to obtain the rest. Our idea behind having incremental improvements was to have a quantitative understanding of the impact of every change. The first microarchitecture, architecture A, uses 4 stages. Block 1, the RFB, which is realized using a direct from structure, and the Pmax Ramanujan filter will thus use LPmax number of multipliers and LPmax minus 1 number of adders. L is referred to as the localization parameter. Smaller L means better time localization but a poor period resolution, and vice versa in the output period versus time plot. Block 2, divider. Here we use a non-restoring algorithm for the fixed point division as it has inbuilt support for signed arithmetic. The divisor is a fixed value for a given channel f of p, which is the penalty function helps to extract the smaller periods with greater strength. Block 3, squarer, which is made using a combinational multiplier. Block 4, moving sum filter, which is also realized in a direct from structure with a smoothing parameter s, which controls the time spreading of strength corresponding to period p in the period versus time plot. The output yin of channel I gives the measure of the strength of period I in the input x of n, and the strengths of the periods are plotted with time to get the period versus time plot. In architecture B, we modify the filter structure of block 1 and block 4 to reduce the critical path delay of the structure. We use the transposed realization structure because they are self-pipelined
To VLSID 2021. I am Sriharsha from SRAM Design Team MediaTek Bangalore, and I am going to talk on the 5 nanometer wide voltage range, the high
The
density
floor is
SRAM
now
design
open
for
for
the L2
questions.
and L3
Hello.
Hello, we'll not do any question answer kind of things, something. So we should say something that flourish for question answer. Now the participant can ask questions to speaker kind of thing.
Yes, yes, we have to do that. So we do that, and then
Actually, session chair will actually handle that thing. So um, my work is actually I need to read the questions, but from this Parman survey today, I anyhow we are not getting any questions.
yes, yes. So now I'll just play another video. So
Yeah.
so we assume that the one session went fine. We did a Q and A, and now we are on to the second paper.
So our main thing is actually means first my work or your work we need to first introduce our session chair. Then he will take over the things and he will call speaker one after another. Speaker need to be
Millimeter wide voltage range, ultra high density SRAM designed for the L2 and L3 cache applications. First, I will introduce the cache SRAM and the high density bit cell. Then I will see challenges in the L2 design, mainly write assist and the self time. I will go through the problem statement and solution for each one of them and discuss on the results and the conclusion. So here we have a CPU core. Whenever it need to access any data from the main memory, instead of accessing it directly from the main memory, which is time consuming, it stores the data in the different cache levels and accesses it. So here L1 is generally the fastest and L3 is the slowest cache. Generally, SRAM is used as the cache because it is the densest storage element in that particular technology. In the SRAM, we have the bit cell array and the periphery logic. So this is the sample 60 bit cell. So in bit we have two variants. One is the high current and other is the high density. For our L2 cache application, because the size is high and also the frequency is less than L1, we are employing the high density bit cell. So here I have a HD bit cell. To write into this bit cell, I need to discharge my bit line from 1 to 0 so that the bit flips from 1 to 0. So on this graph I have the write margin at the SFG corner. So what write margin tells is it quantifies the writability of the bit cell. What it means is whenever bit line is discharging from 1 to 0, the voltage at which the bit cell flips is actually the write margin. So here on the x-axis I have the voltage from 0.45 to 1 volt and y-axis I have the mean by sigma. So what this graph is telling is basically whenever my voltage is above 0.7 volt, we can see my mean by sigma is 7. That means I am able to guarantee the 7 sigma yield. So similarly, when the voltage is below 0.7, the mean by sigma is less than 7. That means I will not be able to guarantee the 7 sigma yield, and we will be requiring the assist for the yield improvement. So there are different write assist technique: word line boost, VDD collapse, VSS boost, and the negative bit line. So all four of them either increase the pass gate strength and the pull or reduce
Good morning, everyone. So, in this part of the session, I'm going to speak about our paper on creating fast self-timing reference path for high-speed memory designs. So, let me start with a bit of motivation. What actually prompted us to work on this idea. So, as we know, the advent of 5G mobile technology has proven this over the time that we really continue to push for high-speed mobile systems. And typically these systems actually are not running at high speed all the time. They actually go in a high speed burst followed by idle time to conserve power for battery powered applications. So, and which is very well served by DVFS technology that we have, based on which we can alter the frequency of operation with the change in voltage. But important thing to note is that the as we are able to scale the speed for these mobile processors, it is very important that we are able to do the same scaling for the interface designs like SRAMs, which is important that they actually scale good in line with these processor speeds so that we could achieve the desired throughput that we are looking for. Okay. So in this paper, we would like to show what actually limits memory speed as we increase the voltage of operation, and try to come up with a solution without actually compromising on these design robust solutions that memory designs use. Okay, let me quickly go through the basic read memory operation just to show where exactly it is limited. So this is starting with clock, and then we have intent clock generated based on which the entire read and write memory operation would work. We enable word line, and then we enable this stop clock signal. It is actually indicating the duration of read write pulse that a particular instance size would require. So which means this stop clock generation would actually depend is dependent on the instance size overall. So once it is generated, then it actually resets the internal clock, ensuring that that would be sufficient for the operation for that particular instance. Okay. Then we enable sense amplifier, and then followed by output send to queue. Okay, so if you look at it in a nutshell, that the clock to queue path is mainly divided into these three subsections. So clock to word line and the sense amplifier enabled to queue output, those are mostly combinational logic which would scale well with increase in voltage. Okay, but there's this third component, that word line to sense amplifier enable, which consists of the self-time replica logic, which is important for the proper read and write pulse to be created. Okay, and that's where the most of the RC element is involved. So that might not scale as good as the logic scales. So that's where the real problem is. That should we actually remain with the design robustness that those RC elements are bringing in, or we could find a balance. So that's just what we are actually trying to see. So let me just put it a little more details. So op clock is actually that internal clock which I was talking about. So if you look at this diagram, so once this clock is generated, we have some logic delay, and then there's the driver, which is similar to the word line driver we would have, and then you would see this horizontal section. So where we have these
Good morning, everyone. I am Firaz Hussain. It is my honor to present my research work in the 34th International Conference on VLSI Design. My topic of presentation is zero point 0.4 microampere offset, 6 nanosecond sensing time, multi-level sense amplifier for resistive non-volatile memories in 65 nanometer LSTP technology. Authored by Firaz Hussain, Bilal Iqbal, and Dr. Anuj Grover. Since every research is built on motivation, we are not apart from it. Physical limitations in scaling of non-volatile memories necessitate alternative ways to increase on-chip storage density. And new generation NVMs offer advantages in terms of speed and can enable replacement of embedded volatile RAMs. Further, storing multiple bits in a single cell enables reduction in cost per bit. Therefore, we studied various essential sense amplifier design techniques such as offset voltage cancellation, double sensing margin, strong positive feedback, etc. to achieve a parallel sensing multi-level sense amplifier for resistive non-volatile memories with faster and stable read operations. First, I will cover basics of the offset cancelling current-based sense amplifier, then design of the enhanced OCCP SA. Thereafter, multi-level sense amplifier design for resistive non-volatile memories, followed by comparison and conclusion. Offset cancelling current-based sense amplifier involves two-phase sensing operation. One is pre-charge phase P1 and second is amplification phase P2. At the beginning of pre-charge phase, switches S1, S2, S3 and S4 are turned on while two switches DS1 and DS2 are off. The diode connected transistor M1 and M2 provides precharge current I pre1 and I pre2 to the bit line and dummy bit line along with ICEL and IREF. Despite the process variation in M1 and M2, current IM1 and IM2 becomes ICEL and IREF after enough precharge time. At the end of P1, cell voltage V cell and reference voltage V cell are stored in capacitance C1 and C2 respectively. In the amplification phase, the four switches S1 to S4 are turned off while two double sensing margin switches DS1 and DS2 are turned on. The introduction of these two switches serves as data dependent reference generator and generates strong positive feedback. The transistor M1 charges this node V cell with the current IM. At the same time, the switch DS1 will discharge this node V cell with the current IREF. Therefore, the total current difference between node V cell and node Vref will be twice of delta I, where delta I is difference between I cell and IREF. Simulated waveform for the case when I cell is less than IREF is shown in the figure. When ICEL is less than IREF, it leads to an increase in VREF that causes lowering of IM1 due to AC coupling behavior of C2. Eventually, this IM1 lowering leads to a monotonic decrease in V cell, which is shown in this figure. Hence, a combination of double sensing margin and strong positive feedback in OCCP assay result in a faster sensing time.
Good afternoon to dear madams and sirs and my fellow friends. Myself, Shambhavi Mitra, Assistant Professor in the Department of Instrumentation and Electronics Engineering from Jadavpur University. I am here to present my paper titled A Low Latency Stochastic Square Root Circuit. I am thankful to my fellow mates, fellow co-authors, Debojyoti Banerjee and Professor Mina K. Nashkar to bring this paper in this present form. Now, the stochastic computing has shown promise over the years due to its relative simplicity in hardware design, enabling low power compared to the conventional computing paradigm. The error tolerance and the hardware efficient solutions of SC have made it extremely popular in a variety of applications, starting from low discrepancy sequences to image processing tasks. In SC, a number is being represented in a string of ones and zeros, where the numerical value is given by the total number of ones occurring in the bit stream divided by the length of the stochastic bit stream. For example, a number within the range, which is obviously 6 by 8, can be represented using the bit stream 110111011. There can be several other representations of it. That means there is a shuffling of the positions of 1 and 0 which can be permitted. Thus, SC, unlike the binary weighted encoding scheme, where each binary bit is associated with a weight and most significant bit carries the highest weight. Therefore, any change in the MSB position will greatly affect the overall decimal value. But in contrary to that, in stochastic computing, the numbers are represented in probabilities, and there are no such weights assigned to the bits such that if any one of the bit gets flipped, then the total number of then the total change is depicted in the average value, that is the number of bits being flipped. One of the most useful applications of the stochastic computing is obviously the multiplication, which can be done using a simple AND gate. For example, a number with probability px is equal to 6 by 8 represented using the bit stream 11011011, and a number with a probability value p4 by 8 can be represented using the stochastic bit stream 100111001. Then the output bit stream can be obtained by just ANDing the two bit streams, which is nothing but 100111001, which is equivalent to pz is equal to 4 by 8. Now, coming on to the square root, which is the material to concern in this manuscript. It is widely used as one of the important arithmetic operators in several operations like calculations of standard deviations, solutions to nonlinear equations, and used in several image processing algorithms. Now, there are few notable implementations of SSRC, and the first one accounts to the circuit that has been realized by Gaines in 1969 using an ADDIE block. It is nothing but a counter with negative feedback to minimize the error between the square of the obtained square root value and the actual value of the number. One of the major disadvantages that this circuit faced was the slow convergence requiring multiple iterations to get to the square root value, which restricted its use in real-time applications. To overcome these disadvantages, Torah later proposed a circuit in which multiple random number generators were used to eliminate the correlation between essence. Thus, the squaring operation could be accurately performed, but at the cost of increased hardware complexity.
We have finished all 5. Hello.
Yeah. I think it's done. 12:25.
Hello. We have already finished all 5. I think so.
Yes, we finished the 5 videos. From tomorrow, I think we will mostly talk on phone. We will not use this WebEx stream, just use it for videos. And the question answers, whichever you guys are, we will be speaking to the speaker. But if internally I need to communicate with you, I'll just communicate you through WhatsApp, or I'll call you separately.
Yeah. So WhatsApp or separately
correct,
call also. WhatsApp is better. WhatsApp is better because it will be without any noise.
Just check if he's playing the.
WhatsApp message will be quick.
Just check if he's playing.
You are playing the video anyway?
No.
You don't hear echo.
All right, fine. So I'll just end this meeting. Tomorrow it will exactly like this, but it will just be for one. So it will just be like this, and it will just be for longer duration.